Welcome back to the Engineering Lab. Listen, if you've been studying Cambridge IGCSE physics, you've inevitably encountered it. You know exactly what I'm talking about, the official equation sheet. It is a dense, incredibly packed, and honestly a sometimes downright intimidating list of formulas that govern our entire physical universe. But what if we completely shifted our perspective today? What if we looked at it differently? Today, we are going to transform this terrifying list of random letters and mathematical symbols into a logically organized, stress-tested, and easy-to-use physics toolkit. By the end of this exam strategy explainer, you are not just going to see a boring list to memorize. No way. You are going to see a collection of specialized, highly effective tools designed specifically to help you unlock the answers to literally any physics exam question Cambridge throws at you. Let's get started. First things first, I want to completely validate your feelings here. If you look at the raw syllabus sheets, especially for subjects like the O625 syllabus, it looks exactly like a foreign language. It is quite literally a wall of equations scattered everywhere without any obvious flow. You've got acceleration, orbital speed, specific heat capacity, refractive index. They're all stacked on top of each other in a way that feels completely overwhelming. It's like a giant puzzle where all the pieces are the exact same color. It is perfectly normal to feel a bit of panic when you first scan through this. But here is the absolute secret to physics exam mastery. We don't have to tackle the whole wall all at once. We are going to systematically dismantle it, brick by brick, until it all makes perfect sense. To conquer this wall today, we're following a precise 5-step agenda. First, establishing the physics toolkit. Second, exploring motion, forces, and pressure. Third, diving deep into energy and thermal physics. Fourth, mapping out electricity and waves. And finally, number 5, connecting all the equations together. Okay, section 1, the physics toolkit. Let's set the foundation. Before we continue and really get into the weeds of these mechanics formulas, I need you to do something. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, got it? Awesome. Let's jump back into the toolkit. Moving right along to section 2, motion, forces, and pressure. All right, this right here is our very first major domain. We are grouping together all the foundational equations that describe how things move, how they interact, and how they push against each other in the physical world. Notice how looking at these fundamental mechanics formulas together reveals a really brilliant hidden pattern. Take speed, for example. The formula is v equals s over t. Speed is just distance divided by time. Then you have acceleration, which is a equals delta v over delta t. Or weight, which is a huge one, w equals m times g, mass times gravity. Momentum is simply p equals m times v, mass times velocity. And finally, pressure is p equals f over a, force divided by area. Whether we're calculating the speed of a racing car, finding the weight of a heavy object, or figuring out the pressure a solid block exerts on the ground, we are constantly using the same core set of ingredients over and over again: time, mass, distance, and force. These are your everyday reliable tools for understanding the physical space around you. Now I want to quickly pause and clear something up that trips up so many students. As you look through the formulas, you're going to see a lot of triangles. That little triangle is the Greek letter delta. Please do not let it panic you or make you think this is some advanced, impossible university-level math. It simply means change in. That's the whole shebang. So when you see delta v, it just means the change in velocity. When you see delta t, it just means the time taken or the change in time. It is literally just a shorthand symbol designed to save you from writing out change in every single time. Let's move on and see how this basic foundation builds into our advanced mechanics tools. Grouping these formulas together shows us exactly how force scales up in the real world. Let's look at resultant force. F equals delta P over delta T. That's just the change in momentum over time. Then there's impulse, which is F times delta T equals the change in mass times velocity. If you need to know the turning effect of a force on, say, a door hinge, you reach for the moment equation, force times perpendicular distance. And what if you need to know how force relates to the stretching of materials? You reach for the spring constant tool, K equals F over X, force divided by extension. Do you see the pattern? They are all just clever variations of pushing, pulling, and turning things. It's all connected. All right, section 3, energy and thermal physics. Transitioning away from visible motion, we are now entering the realm of the hidden forces of the universe. We're talking about how energy is stored, how it's transferred from one place to another, and how it dramatically affects temperature. Let's look at the toolkit for this. Kinetic energy is delta Ek equals 1/2 mv squared. Potential energy is delta Ep equals mg delta h. Look at power. P equals delta E over T. Now observe how all these equations inherently link back to the transfer of energy. Whether it's the kinetic energy of a speeding train or the potential energy of a massive boulder resting at the top of a hill, it is all about energy in different forms. Stop scrolling, subscribe to our YouTube channel Ace the Exams at acetheexams_IGSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @theexams_IGSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, now look incredibly closely at the work done equation derived straight from the sheet right here. Work equals force times distance, which equals delta E. This brilliantly proves that mechanical work and energy transfer are essentially two sides of the exact same coin. Whenever you do work, you literally change energy. Simple as that. Now, I'm going to share a massive exam hack about the official equation sheet itself. It actually lists specific heat capacity twice. First, it writes it all out in plain words, energy required divided by mass times temperature increase. Right below it, it gives you the exact same thing in scientific symbols. C equals delta E over m times delta theta. Understanding this instantly reduces what you actually need to memorize. You don't have to learn two separate formulas for your exam, just the one single concept written two completely different ways. And just like we did with the delta symbol earlier, let's demystify another Greek letter right now so it doesn't catch you off guard. Theta. Whenever you are operating in the thermal physics domain and you see theta alongside delta, it is simply talking about temperature changes. That's it. It is just a specialized symbol we use for temperature, so we don't confuse it with a lowercase t, which, as we know, stands for time. Keeping those symbols straight is absolutely crucial for your exams. Section 4. Electricity and waves. Let's explore the highly structured, almost invisible worlds of electrical currents and wave behavior. In this domain, you're going to see how these foundational electrical equations all build logically upon one another. Everything, and I mean everything, revolves around three main things: charge, represented by Q, work done, represented by W, and the flow of that charge, which is current, represented by I. Look at the formulas. Current is I equals Q over T. Electromotive force, or EMF, is E equals W over Q. Voltage, or potential difference, is also just work done per unit charge, V equals W over Q. Resistance is just voltage divided by current, R equals V over I. And even the potential divider equation, R1 over R2 equals V1 over V2, follows this logic. Once you see that they all share these exact same core building blocks, the electrical section of the sheet feels much less like random, confusing circuitry and way more like a predictable, connected system. This brings us to a massive, massive distinction you have to make in your exams. The formula sheet gives you two different formulas for electrical power. One is total power, which equals current times potential difference, or P equals IV. The other specifically says power loss equals the square of current in the cable times resistance, or P equals I squared R. Knowing exactly when to pull out the total power tool versus the power loss tool is an incredibly important distinction. Mixing these up is a common trap, but knowing the difference will absolutely save you marks on tricky exam questions. Next, we group the remaining equations from this domain into what I like to call the ratios and waves section. Consider the formulas for transformers and the bending of light. For transformers, the voltage across the primary coil over the secondary coil equals the number of turns on the primary over the secondary. That's Vp over Vs equals Np over Ns. Power in equals power out, which is IpVp equals ISVs. Wave speed is V equals F times lambda, and the refractive index is just the sine of the angle of incidence over the sine of the angle of refraction. N equals sine I over sine R. So the crucial takeaway here is that simple, elegant proportional ratios govern both powerful electrical transformers and the way a simple beam of light bends through glass. Finally, Section 5, connecting the equations. Now that we have completely organized our toolkit into logical domains, mechanics, energy, thermal, and electricity, let's look at the exact procedure to follow when you are faced with a really complex problem that's clearly trying to confuse you. When you read a tough problem, do not panic. Follow this simple 3-step procedure. Step 1. Write down the variables the question explicitly gives you. Let's say you have a mass and a speed. Step 2. Write down the specific variable you need to find. Maybe the question asks for kinetic energy. Step 3. Look at your newly organized mental toolkit and select the equation that contains exactly those variables. In this specific case, delta Ek equals 1/2 mv squared. It's like fitting a key into a lock. This logical step-by-step path prevents you from guessing and leads you to the right formula every single time. But here is where you really separate the good physics students from the great ones. You absolutely have to recognize the variables that cross between domains. Time, for instance, is everywhere. It's in speed, it's in power, it's in electrical current. Mass bridges both motion and thermal physics. And energy spans literally everything on the entire syllabus. So the crucial point here is that because these variables cross boundaries, you can confidently link a mechanics problem to an electricity problem using those shared terms. If you know the mechanical work done, you can easily figure out the electrical energy transferred. They speak the same language. I want to leave you with a final challenge to test your brand new toolkit. Imagine an exam question gives you a mass of water, the height of a huge waterfall, and the time it takes for that water to fall. What sequence of equation tools do you need to pull out to calculate the mechanical power generated? Well, think about how you would first combine mass and height using the potential energy formula, and then bring in time using the power formula to solve this whole thing. Consider how mastering this structured toolkit changes absolutely everything. You aren't just blindly memorizing a wall of text anymore, you are engineering real solutions. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep practicing with your tools, and I'll see you in the next explainer.